Hypothalamus Artificial Intelligence, HI, and Research Center for Advanced Decision Technologies, RCADT, a division of HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Present the conference. Benders Dual Decomposition. The material of conference was organized by the engineer Jesus Velasquez Bermudez, Ph.D. Since its formulation in 1962, the researchers in Benders theory, BT, have proven that BT is an effective methodology to solve complex problems that cannot be solved using only best basic optimization algorithms, PLEX, Gurobi, Express. Algorithms based in Benders theory can solve NP-hard, non-deterministic polynomial time problems in reasonable time. For this type of problems, BT has proven to be an effective methodology to solve complex problems that cannot be solved using best mathematical solvers. BT is a mature methodology that is in the accelerated growing phase, and there is a gap between the research in mathematical programming and the application of the large-scale methodologies in real-world solutions. This presentation focuses on Benders theory for discrete subproblems. This presentation focuses on Benders dual decomposition. Benders dual decomposition. Ramanayani et al. Formulate BDD by applying Lagrangean duality to subproblem reformulation to evaluate coupling constraints that link local copies to master variables. BDD integrates BD with LDD to solve large-scale problems of integer mixed linear programming, MILP. BDD generates significantly stronger viability and optimality cuts than classical methods. The main IBDD enhancements are cut strengthening. BDD uses local copies and dual pricing to generate cuts that provide a tighter lower bound earlier in the iteration process. Scenario parallelization. By enabling scenario-based decomposition, BDD is highly effective for large-scale stochastic problems, allowing for efficient parallel computation. Hybrid mechanisms. Modern implementations often integrate BDD with other techniques. Local branching improves both lower and upper bounds simultaneously. Machine learning. Recent 2024 papers explore ML-enhanced Benders to solve multi-stage stochastic optimization problems faster. Pareto optimal cuts. Techniques based on the Mignati-Wang method to select the strongest possible cuts from alternate optima. The image shows two parts of BDD's original post. The introduction and proposed method for BDD. The image shows the BDD publication of Chapter 2 of Velasquez Bermudez. It is important to note that the optimality and feasibility cuts, including values of subproblem primal variables, are like the case of generalized Benders decomposition, GBD, then it is possible call this type of cuts as generalized Benders cuts, GBC, that include dual and primal variables of the subproblems. This approach produced strongest cuts that standard Benders. Below are the cases analyzed by Ramanayani et al. To test the convergence and acceleration of BDD. Three types of problems were tested. FMCND, Fixed Charge Multi-Commodity Capacitated Network Design, CFLS, Stochastic Capacitated Facility Location, and SNI, Stochastic Network Interdiction. Feasibility and optimality cuts are generated by solving each subproblem within a 0.5% optimality gap. To generate the Lagrangian cuts for the FMCND and CFLS instances, the partially relaxed subproblems approach is applied. Ramanayani implemented 4 variants of the strategy. BDD-1, using strengthened Benders cuts by imposing the integrality requirements on all the copied variables. BDD-2, using strengthened Benders cuts by imposing the integrality requirements on a subset of the copied variables. BDD-3, like BDD-1 but also generates Lagrangian cuts. BDD-4, like BDD-2 but also generates Lagrangian cuts. The table shows the relative speedup of the 4 BDD variations compared with standard Benders, BT, and Lagrangean Dual Decomposition, LDD. The advantage of BDD in computational time, and in the quality of the gap, is evident. The table shows the relative speedup of the 2 BDD variations compared with Plex. The gap tolerance was 1%. It should be noted that Plex failed to meet the gap tolerance, and in such cases exhausted the maximum processing time. The column #sol indicates the number of solved problems over the total of problems. Generalized Benders cuts, GBC, are valid inequalities used in Generalized Benders Decomposition, GBD, and Benders Dual Decomposition, BDD. Like the original method, GBCs are added iteratively to a master problem to refine the approximation of a complex subproblem. There are two GBCs. Optimality cuts. Feasibility cuts. How is GBC different from classical Benders? Problem class. GBC allows the subproblem to be a nonlinear or integer. Duality theory. Classical cuts rely on linear programming duality, dual variables. GBC uses nonlinear convex duality, Lagrange multipliers, to derive cuts from the subproblem's optimality conditions. Classic cuts are composed solely of dual variables, while GBC contains dual and primal variables. Key applications and advances in 2025. Recent developments highlight the use of GBC in complex stochastic and large-scale optimization. Stochastic MILPs. GBC is central to new branch and cut algorithms for two-stage stochastic programs with non-convex constraints. Hybrid approaches. Modern implementations often combine GBC with Lagrangean cuts or other cutting planes, like McCormick envelopes or lift and project cuts, to handle non-convexities more effectively. Automation in solvers. Leading optimization suites like IBM Plex and SIP have automated many aspects of Benders decomposition, including the generation and management of these cuts. GBCs are derived by projecting the original problem onto the space of complicating variables, usually discrete variables. By fixing these variables, the remaining subproblem becomes easier to solve. The dual information from this subproblem, specifically the subgradient or multipliers, defines the slope and intercept of the cut added to the master problem. As in the standard Benders method, a subproblem, Q of y, is defined to indicate the objective function of the slave problem. In this way you have two problems, master problem and slave problem. The slave formulation is different in BDD and includes a copy of variables, z equals y. The cut entered into the master is of the generalized Benders cuts, GBC, type. The structure of the redefined problem is presented below. The two problems, BDD and standard Benders, have a similar structure, but only BDD can handle discrete subproblems. A structure of two levels is established to solve the problem. First level is the equivalent problem in terms of y, that is designated as the coordinator. Second level is a subproblem for the variables x and z that generates cuts for the coordinator problem. The solution is obtained by exchanging information between the coordinator and the subproblem. The coordinator proposes primal variables and the subproblem generates dual and primal variables. Performance of different cuts in cutting the solution space of LP master problem. To illustrate the benefits of the proposed method, consider following toy problem. The optimal solution to this problem is y equals 0, which has a cost of 8 units. BDD solve the LP relaxation of this problem using the classical, strengthened, and Lagrangean cuts. The figure shows graphically depicted the cuts generated at each iteration of these methods in the y, theta, space. In solving the LP relaxation of the master problem with the classical Benders cuts, after 5 iterations the method converges to the optimal LP solution, y equal to 0.58, and its objective value of 2.4 units. If the strengthened Benders cuts are used, then the first 2 iterations of the algorithm generate the same cuts as the classical ones. The reason for this is that the y solutions for these 2 iterations are integer and as a result the Benders cuts are the strongest. At the third iteration, solving the MP produces the solution, y equal to 0.65, the associated strengthened Benders cut is parallel to the classical Benders cuts but tighter by 6.125 units. At this point, the proposed method with the strengthened cuts converges. For the master solution, y equal to 0.65, the Lagrangian cut provides the convex Hull representation of the MP and, consequently, the algorithm converges to the optimal integer solution. In this case, while solving the LP relaxation of the MP, the optimal integer solution is obtained. In case that feasible solution X does not exist, Then the following feasibility subproblem must be solved, and the feasible cuts are called as dual Benders cutting planes for feasibility. In Table 1, both the time requirements and the percentages of the root gap are reported for the BD, LDD and the 4 variants of BDD. These experiments are obtained by assigning a maximum duration of 1 hour. These results were obtained by applying the BDD method together with the proposed optimality cuts together with the classic feasibility cuts, to analyze the isolated impact that the reinforced optimality cuts have on the overall solution process. When analyzing the results in Table 2, generating reinforced feasibility and Lagrangian cuts has less impact on the narrowing of the root node boundary, compared to the inclusion of the proposed optimality cuts. This was to be expected, given that feasibility cuts do not limit the variables in the master problem. The generation of feasibility cuts increases the time requirements. For this reason, a deterioration of the holes obtained in root node gaps is observed. It can be anticipated that the proposed feasibility cuts will be most beneficial for problems where finding feasible solutions is a challenge. Given the marginal impact of these cuts in this case, from now on only the classic feasible cuts are used to solve FMCND instances. The Table 3 shows that the upper bounds obtained by the BDD3 variant are very close to the optimal solutions. Compared to BDD4, BDD3 finds better upper bounds, which can be explained by the fact that, in this variant, the integer requirements are imposed on all the variables copied in the subproblems. Thus, it generates more complete solutions. Similarly, given their respective definition, BDD3 and BDD4 offer a much larger set of complete solutions compared to the BDD1 and BDD2 variants. Consequently, these variants considerably improve the quality of the upper limits generated. In addition, the upper bounds obtained by BDD3 and BDD4, except for FMCND instances, are much better than those generated by the LDD method, indicating that BDD provides an improved search mechanism. Last but not least, the quality of the primal bounds shows that the proposed improvements significantly alleviate the primal inefficiencies of the BD method. The table presents the performance of other experiments in which the comparison of multiple technologies is presented. Plex is included as an example of a monolithic model, solved with one of the best commercial solvers. The table includes the speed relationship between Plex, Benders standard, and BDD. These proportions are BDD 5 times faster than Plex, and Benders 1.62 times faster. Improved Benders Dual Decomposition. Case, optimal sizing problem of power to ammonia. The BDD method is affected by the duality gap due to the non-convexity of the second stage problem. To mitigate this, in 2024, Suchau, in the article An Improved Benders Dual Decomposition Method to Solve the Optimal Sizing Problem of Power to Ammonia introduces the Bundled Lagrangian Cuts, BLCs, a novel type of optimality cutting based on the packaging of random dissimilarity scenarios. The optimization problem was formulated as a two-stage stochastic mixed integer program, SMIP. BLCs establish a tighter convex approximation of the second stage cost function, enhancing the lower bound provided by the master problem. Building on BLCs, Suchau proposes the improved Benders Dual Decomposition, IBDD, method. The first stage determines the capacity combinations, while the second optimizes the schedule. This problem is difficult to solve due to the need for numerous scenarios to capture the stochasticity of renewable generation and the presence of discrete variables representing the on/off states of production modules, leading to a second-stage non-convex problem. IBDD demonstrates its ability to solve large-scale SMIPs, which are fundamental optimization problems in many renewable energy systems, without requiring spatial branching of first-stage variables. The electricity supply for power to ammonia plants, called TA, is primarily sourced from co-located renewable power plants, supplemented by a minor portion from the public grid. The optimal planning and integration of large-scale TA plants in power systems attracts increasing attention from the power industry. TA plants are composed of various electrochemical and mechanical processes, and multiple energy/feedstock storage facilities, each with a distinct operational envelope and cost structure. One of the tasks during the engineering stage of a TA plant is to determine the capacity values of different production and storage modules with the objective of minimizing the overall cost of ammonia production. The capital expenditure, CapEx, of TA plants typically accounts for 40% of the end product cost breakdown. Finding the optimal combination of different modules in a TA plant is a determining factor in its financial success. The TA plant is mainly composed by electrolyzers split water into hydrogen and oxygen. Air separation units, ASUs, extract nitrogen from air, and Haber-Bosch, HB, reactor binds hydrogen and nitrogen into ammonia. The production modules have different levels of operational flexibility. Electrolyzers are very flexible in operating range, ramp capacity, and on/off transitions. In contrast, ASUs and HBs are less flexible due to their need to maintain a fine thermodynamic balance. To stabilize the operation of TA plants and respond to the variable renewable energy, hydrogen and nitrogen storage facilities normally necessary to ensure a relatively stable feedstock for the HB reactor are used. Electrical storage facilities can also be used to optimize local electricity use and reduce carbon emissions. The figure shows the schematic diagram of a TA plant. The variables in the parentheses are the sizing variables to be solved. During the engineering stage, the focus is on determining the sizing variables, while the optimization of the second stage estimates the expected operating costs associated with different capacity combinations. Two cases, based on the feasibility study of real projects, are used for the computational exercises. FTA case, a PV-powered TA plant with a co-located 300 MW PV plant, annual capacity factor is 0.20. The grid connection has a constrained capacity of 20 MW. FTA case, a wind-powered TA plant with a co-located 180 MW wind farm, annual capacity factor is 0.34. The grid connection has a constrained capacity of 20 MW. The hourly generation profiles of photovoltaic and wind power plants are synthesized using renewable engineering software based on historical weather data. The goal is to find the optimal combination of the sizing in these TA plants. The installation cost, operational cost and constraints of different modules and storage facilities are given in Table 3, Table 4, and Table V. These cost assumptions are based on feasibility study reports and cross-checked with existing literature. Two cases, based on the feasibility study of real projects, are used for the computational exercises. FTA case, a PV-powered TA plant with a co-located 300 MW PV plant, annual capacity factor is 0.20. The grid connection has a constrained capacity of 20 MW. FTA case, a wind-powered TA plant with a co-located 180 MW wind farm, annual capacity factor is 0.34. The grid connection has a constrained capacity of 20 MW. The hourly generation profiles of photovoltaic and wind power plants are synthesized using renewable engineering software based on historical weather data. The goal is to find the optimal combination of the sizing in these TA plants. The installation cost, operational cost and constraints of different modules and storage facilities are given in Table 3, Table 4, and Table V. These cost assumptions are based on feasibility study reports and cross-checked with existing literature. Operational constraints of storage modules. Table V. Our results with electricity storage cost half of that in Table 3. We observed a 4.9% difference in the obtained Z value between S equals 12 and S equals 120, indicating that lower representativity of the stochastic generation leads to suboptimality. This also highlights the necessity of using more scenarios in the optimization. Table V gives the results of the FTA case. In the FTA case, only hydrogen storage facilities are required, while electricity storage and nitrogen storage are found out to be unnecessary. Nitrogen storage is exempted due to the ASU's capability to operate at partial load, aligning proportionally with that of the HB reactor. Electricity storage is not needed since the public grid provides sufficient electricity for the operation of all modules except for electrolyzers, which can be easily turned down when there is no PV production. The electricity storage only becomes economically necessary when its installation cost is below 65% of that of table. Capex of S is half of that indicated in table 3. The results are divided into several variables. Cost, NEL, CASU, CHB, CES, VACE, CHS, VHS, CNS, and VNS. The BDD method convergence profile for up to 120 scenarios is shown in the figure. For the PTA case, both BDD and IBDD produce satisfactory results with a relative gap under 0.5%. In terms of solution time, the BDD and IBDD methods use 291 and 206 seconds. For the IBDD method, one iteration of the Benders master problem can produce results with the relative gap lower than 0.5% for all the 4 scenario cases. Solution results of the WPTA case. Due to this fact, the hydrogen storage facility is found to have a larger volume to capacity ratio in the WPTA case compared to the PTA case, namely, 11.4 for the WPTA case and 6.4 for the PTA case. This also indicates WPTA plants usually need a larger storage facility. Electricity storage and nitrogen storage are found not to be necessary. A 4.0% difference in the obtained Z value between S equals 12 and S equals 120 has been observed, also highlighting the need of using more scenarios in the optimization. The Table 8 shows the BDD method fails to reach the relative gap threshold, as shown. In comparison, the IBDD method can reach less than 1.0% relative gap within 1,200 seconds, and less than 30 iteration loops for all the 4 cases, with significant improvement on both upper and lower bound values. The difference in performance between IBDD and BDD comes from IBDD ability to bridge the duality gap. It can be seen the optimal sizing problem of TA plants is a large-scale SMIP in the extensive form. The direct solution of the extensive form is beyond the capabilities of current optimization solvers. The pseudocode for the BDD method is presented in Table I. Improved Benders Dual Decomposition, IBDD, refers to modern algorithmic frameworks that enhance BDD, including a new type of optimality cut, which we call bundled Lagrangian cut, BLC, or strengthened Lagrangian cuts, SLC. IBDD has shown that the target value obtained is better than the BDD method and the dual decomposition method, because BLCs are more compact than the traditional Lagrangian cuts, significantly reducing the duality gap in mixed stochastic integer programming. IBDD includes quadratic regularization that has been shown to be able to accelerate the convergence of the Benders master problem and reduce oscillations around the optimal point. The pseudocode for the BDD method is presented in Table 2. The figures show the ammonia production of the PTA case, A, at the top, and the PTA case, B, at the bottom. It is observed that the ammonia production in the PTA case is more random and uncertain, leading to more frequent startups and shutdowns of the HB reactor, compared to the PTA case. This reflects the consequences of the higher variability associated with wind power. The convergence profiles for the BDD, A, and IBDD, B, methods for the PTA case 60 scenarios. The faster decrease in the relative gap in IBDD is evident. Albert Einstein thought that imagination is the highest form of research. Thank you for your attention.